And so our last speaker is Harry. So Harry's going to talk about Arbitrum. Take it away, Harry.
Alrighty, awesome. So hey everybody, I'm Harry Kalodner. I'm a researcher from Princeton University, and I'm here today to talk to you about a system that we've been developing called Arbitrum, and it's a system to allow for scalable private smart contracts. So just very, very quickly, because we've seen a lot of this stuff 100 times already. What do we like kind of for our model think about as a smart contract? So we have Alice and Bob, and they agree on a set of rules. And they don't trust each other, but they both want to ensure they can work together if they're willing to both follow these rules. So what do? Well, you create you post this to the chain as a smart contract, and we'd consider that smart contract a virtual trusted third party. So now Alice and Bob have this other entity that they both can trust, and they can interact using this now trusted third party, which is the blockchain. And the smart contract, it's trusted to follow the rules, and it's stateful, so you can do interesting things with it. But for it to really have some teeth and be useful, we have smart contracts with a cryptocurrency, and then your smart contract can actually enforce monetary conditions, and where most of the interesting applications come in. So Alice can send money to the machine can get money, can send it to Bob. Essentially, whatever the rules of the contract are, you have a trusted party to interact with. So smart contracts, when we say smart contracts, a lot of time we think about Ethereum. We have a scripting language. We have state. We have to pay gas for computation and storage, and this is because every single computer in the world has to execute all of it, and so you need a high gas cost because otherwise we wouldn't be able to run the network. And so that's a real problem. And so that's kind of the challenges that we're faced against. Every miner needs to verify everything. And so the total amount of work that you need to do in the network is the number of miners times the number of contracts times the average kind of execution that a contract has to do. And so that's a lot of work for a property that in a lot of cases isn't really required. So what are the scaling approaches we can take? How can we kind of get around this issue? Well, there are a number of different approaches. This is just a few. There are definitely more. We could use snarks, do some fancy cryptography, but you're probably going to run into issues doing this in practice. There's a trusted setup with snarks, which is pretty expensive and difficult to do, and just using them in general requires a lot of work. And so it doesn't seem like right now it's a practical solution. There's incentivized verification, and TrueBit and I think some other people are working on similar models where there's an incentive system, and I set it up so that somebody in the world is going to catch me if I lie about what I'm doing. But for this to work, you can't have any privacy, and we really want both scalability and privacy since everybody needs to be able to check your work. And we also, at least in the original paper, demonstrates that there's some incentive compatibility problems with how it's done. And then you have state channels. And state channels are awesome, and we definitely, state channels are one component of our system. Only unanimous progress is not entirely true, as we've seen, but at least if you want to do anything that's not unanimous progress, you have to go fully on-chain. And so your entire smart contract, your entire state machine has to be posted to the blockchain, which is not great for privacy. And it's not great for keeping costs down if a state transition is expensive. And so that dispute resolution can be pretty costly. And it's also something that the application developer has to think of their application as a state machine, which is not the nicest model to think in. So Arbitrum, we think, kind of is a pretty good solution to a lot of these problems. And our approach is a combination of protocol design, incentive design, and a custom VM architecture that we've designed. And so you'll notice that there's no fancy crypto in here, which I kind of like because I think it's a solution that really kind of intuitively can make sense. So now I'm just going to talk a little bit about how Arbitrum works and hopefully convince you that this is a good approach to take. So the main idea between Arbitrum is that we have a smart contract, or I'm going to call them VM, virtual machine, which is kind of the terminology that we tend to use. Apologies for all the different terminology. I mean, as we've talked about today, there's a lot of different terminology between projects, but I'm using what we use here. So a smart contract has managers, and these are kind of akin to participants in a state channel. And when you create a VM, you select the list of managers, and the managers are responsible for tracking the state of that VM, actually executing it, and what we base our entire system on is this any trust guarantee, and this is really important. And what we're guaranteeing is that if any one manager is honest and available at any given time, the VM will execute correctly according to its code. And so if you want to interact with this system, then you just need to make sure that either you're a manager or somebody you trust is a manager. And what this means is that any other VM you can't trust at all. They could be doing anything, which is a little weird maybe, but all it really means is that any other VM to you essentially just might as well be a multi-sig where the people who control it are doing arbitrary things. And so it doesn't really affect you at all. And the only way that another VM can actually affect you is by sending you money, which we're okay with. So how does this VM work? How does this used in practice? So managers are incentivized to unanimously agree. And when you hear the term unanimous agreement, you should think about state channels, and that's what you should be thinking here. And if all of the managers sign a transaction saying our VM has run all this code, everything's great. And so a unanimous assertion, we just start with kind of our beginning state, and so there's some state for our machine, and we just all say the machine executes a bunch of steps, it ends up in this state, and it takes these external actions. And so the machine can send coins, it can send messages, and all of that just happens instantly with signatures by all of the managers. So we send it to the blockchain, and it's instantly confirmed, or well, at whatever rate the blockchain is going, but no challenge period necessary. Now that's all on-chain, and it works nicely on-chain. Our main goal that we started out with was computational scaling. And so here, the VM could execute any amount of code, and there's never going to be any gas costs other than kind of a fixed cost, which is mostly just for data and some stores. And so if we want to scale messages as well, this is where state channels come in. Essentially, we can use the same unanimous agreement, unanimous assertion primitive, and create a state channel style series of messages off chain. I'm just talking single VM, single set of participants. We're not talking about multi-hop here. That's future work. But this is all great, but what if the managers don't agree? And this is where I think that a lot of the state channel solutions break down, because if you have a two-party system, it's fine if kind of that you really need all the parties to be available and agreeing. But if you want to have a 10-party system, then if 9 of the 10 parties are available and agreeing, it's not very fun if kind of you basically have to just go to the chain entirely. So we get around that by a disputable assertion. Now, a disputable assertion is something that only a single manager would sign. And so we can't just accept it immediately. We have to have it subject to challenge. And we have a challenge period. You've heard a lot about challenge periods probably over all these presentations. There's a deposit by the asserter. You put some money down when you say this is honest, that you'll lose if you're wrong. So a little more into like what this process looks like. So here you are, not shown on this slide, but you've put down a deposit. You broadcast it to the network, and a time period starts where this is pending. Now, if nobody does anything, after a certain number of blocks configurable for the VM, it's confirmed, it's accepted, that becomes the new state. Any external actions that are described in that update occur, and the machine just continues to function. Now, what if you lie and you do something bad in this disputable assertion, since you could really say anything, and this is kind of the problem that we need to handle? Well, during this challenge period, any one of the managers is allowed to say, no, that's wrong. and then they enter into a bisection protocol in order to pin down exactly where it went wrong. So they issue the challenge. That's now marked on chain, and that it starts this period. What happens then is that the original asserter has to chop that assertion in two. So they say, well, you executed n steps to get the machine from the state it started at to the state it finishes in. Show me at n over 2 what the state was. I look at that and I say, do I agree with it? Well, if I agree with it, then it must have been the problem was in the second half. And if I don't agree with it, then the problem was in the first half. So I can narrow down exactly at least one place where I disagree with the original assertion. And see here, we split the messages. There's a message on the left side, and there's coins on the right side. And what this is showing is that when you cut up an assertion into pieces, any external actions have to be on one side or the other, because they have to have been triggered by a single instruction in the machine. And so if you dispute some action the machine takes, you just need to narrow it down to a single step and see whether that action actually occurred there. So we pick a side, we continue going down, pick again, and then eventually we're going to get down to a single step of execution. And then there needs to be some way to actually, we eventually need to actually have somebody settle our dispute. We've been arguing about kind of exactly where the dispute is, but now we've kind of gotten it down to the minimum quantity. So pick the side. I have a couple more steps. There we go. Oh, so there we had one step, and now there's this one step that we need to figure out. And so then we need a one-step proof. And when kind of one-step proof, so that's one step of execution of the VM. But that's kind of abstract. I mean, what does that actually mean? And a good chunk of the rest of this talk is explaining what that means and how we make it efficient. And so the big questions are like, do I need to post like 10 megabytes, 10 gigabytes? What do I actually need to put on the blockchain in order to really settle this dispute, considering the fact that there's basically been nothing on the blockchain so far, very little. So how costly are these proofs to create? How costly are they to verify? How big are they? Those are the questions that we need to ask. Well, this is where we use the Arbitrum VM Architecture. And this is a custom VM architecture that we developed specifically in order to make these one-step proofs very, very small and very efficient. And in this architecture, all instructions can be emulated in constant time, which means, or at least in all instructions, no instruction takes a long time to execute, no single instruction. And one-step proofs are of small constant size and can be created and verified in small constant time. And this means that even things like your VM having an arbitrary amount of state and having an arbitrary large amount of code, the amount of state and code you have has no effect on the time to make a proof, which is a kind of counterintuitive property, and it's where kind of the interesting parts of the architecture come in. And so there are four main principles that we came across and that we used when designing this architecture. So the entire state of the virtual machine is in a Merkle tree, so that it's easy to kind of do proofs on this. It's easy to use. That tree is of limited degree, so it's only of size 8, which means that any one unfold is going to be maxed in terms of how much data it has to reveal. And every leaf is of a limited size. And so you can see how right there, kind of we're bounding how much we're ever going to need to post on chain in order to settle something. And the final very important thing is that instructions only affect items near the top of the tree. And so if you're imagining what we would need to reveal to the blockchain in order to settle a dispute, it's a very small amount of information. Since it's just nodes near the top of the tree, your proof is going to be of a fairly small maximum size. But this has some pretty weird implications, as you might have already been thinking about. I don't know. So you can't use this architecture with flat memory, because flat memory you can't doesn't fit those criteria. If you want to have your VM read some random slot in storage, then you're probably going to need some sort of Merkle proof of your entire storage and then reveal a logarithmic path to whatever cell of memory you're using. It's not going to be constant size like we want. And so here's how we solve that. And it's kind of a weird solution, but it really works well in practice. So our VM has types, and one of the types it has is a tuple. And tuples can hold other tuples recursively, so you can imagine how you could very easily build up a tree of values of arbitrary size. We can put this in a library code in order to simulate flat memory, since essentially, if you have a tree, then each of the leaves of that tree could be a slot in memory, and then when you read, you just have to do a logarithmic number of operations in order to get the memory. Since you say you're in this tree, you say go left, go left, go right, go right, go left, and you reach the leaf. And those are all single instructions in the machine, and each one of those instructions is constant size and time. And so what we've done is we've taken something that would otherwise normally be a single instruction that requires a logarithmic size proof, and we've transformed it into a logarithmic number of constant size steps. So what does this architecture look like, kind of quickly? So it's not that weird. We have our state root, which encodes the entire state of the machine, and then it just has a few pieces to it. We have an instruction stack, which stores what instructions the machine executes. We have a data stack, which is just your typical stack. We have a call stack for making calls. Static data that you set up the VM up with that can just be an arbitrary large amount of data that never goes on chain. And a single register that the machine can use. And so we have this very, very minimal amount of state that has to be encoded to have an arbitrarily complex virtual machine running your contract. And so just one very specific example of what a single one-step proof would look like. Here we have a proof of an add instruction. So how do we prove that if you added wrong, how do I prove that you added wrong? Well, first of all, we need to confirm that you actually were supposed to add. Maybe you were supposed to multiply. And so we reveal what the next instruction to execute would be, which was add. We also need to reveal the first two items from the stack. We have mostly stack-based architecture, so all of the opcodes use the stack. And so we reveal the top two items, a 5 and a 3, and that's it. The call stack doesn't matter, the static doesn't matter, the register doesn't matter. You just need to reveal kind of the minimal amount of information, and proof confirmed, we've solved it, you added correctly. So that's one example of what a one-step proof would look like. And any proof would reveal a similarly small number of items from the machine. So the one effect of this architecture and this style of functionality is that we really have a pretty substantial amount of privacy in smart contracts. And I would say substantially more than kind of a lot of the state channel style approaches. And the reason for that is because even in a dispute, as I just showed, you have to reveal a very small amount of data. And what we can promise is specifically that if the managers behave according to incentives, the internal state of a VM will never be published. And a manager could always voluntarily leak. So in this model where everybody who's a manager knows everything, or everybody in the state channel knows everything, you can never have privacy from each other until you start using some very impressive cryptography that we saw in the previous talk. But you do have to leak a small amount of information, because we are doing these one-step proofs. You're revealing a little, but we can get around that too. And that's pretty easy to do. We haven't designed it yet, but we're sketched it out, and it seems pretty straightforward. You can just all you need to do is transform this single one-step proof into a zero-knowledge proof. And even when challenged, there's still no leak on chain, even though a challenge should never happen anyway. And so we don't think that this would really be a problem in practice. But if you're worried about it, zero knowledge works pretty well. And you would only need to design a single zero knowledge circuit in order to secure all of Arbitrum VMs, since the proof is for the entire architecture, not any specific contract. So what have we actually implemented so far? So we've kind of have some initial implementation in Go. We have an emulator for the VM architecture, an assembler and loader for kind of setting it up with code. We have an implementation of an honest manager that can make and defend assertions. And that's all kind of independent of any real consensus mechanism. That's just kind of what you need on the user end in order to work with this type of system. And I'll talk a little bit more in a bit about kind of actually putting it into practice. We have kind of our own. We have an Arbitrum assembly code that you can use in order to write for these VMs, because all people really need to write code is assembly. Who needs higher level programming languages? But programming tools are currently a work in progress since we have this kind of exotic VM architecture. So just kind of an example of performance and why kind of this is nice. The thing that we're really interested in is computational performance, and that's an area that really we get to show off in. I'm going to say this with the caveat that just like Ethereum has a native hash opcode, we also have a native hash opcode. So the actual implementation of hashing is done in native code. But essentially, we can perform at least a couple orders of magnitude more hashes per second than Ethereum, and that's in one VM. Whereas Ethereum, we're talking about a global limit. Here, each VM can execute in parallel, doing a very, very large amount of computation. And so if you have any sort of contract that you couldn't really run now because you're worried about gas costs, because you want to do something that's a little too complex in terms of amount of state or amount of computation that can't really work with current models, this is a model you might want to use. So in terms of applications of this, well, I mean, most smart contracts, I think a lot could benefit from this as long as the AnyTrust model that we use is kind of interest and will work for your use case. One interesting application of this that I kind of like is virtual private blockchains. So these are private blockchains-ish, but with on-chain dispute resolution. Because the biggest problem that I see with private blockchains is, what if something goes wrong? What if the main people managing it disagree? You don't really have a very good way around this. What if they try to censor? You don't have a really good way around this. And so some sort of kind of hybrid architecture where you take advantage of the private state of Arbitrum VMs in order to keep all your transactions private in your private blockchain, but still can go on chain for dispute resolution and anti-censorship, I think could be a really cool solution. So Arbitrum is a very versatile design. We're consensus independent. We don't really have any interest in the consensus layer. So one great implementation of Arbitrum is on top of Ethereum. I think really any smart contract platform could implement Arbitrum if it can implement the one-step interpreter. I think that it might be interesting to have it as a kind of a base level for an entire blockchain just doing these. We're looking at Ethereum. I mean, that's kind of what we're doing to start, but I think it's a very general architecture that could benefit a lot of places. An actual implementation of the smart contract is a work in progress. I wish I could tell you the actual gas cost of one of these one-step proofs, but they're very, very quick to run on a computer. So if we can figure out how to write enough assembly and solidity, it should run quickly with low cost. And one interesting point I'd like to make, and I think this holds true, and I've talked to some people who I think buy this idea. I think that Plasma might be able to benefit pretty nicely from our VM architecture, just because of these really nice proofs that you're able to produce of correctness. So yeah, just to conclude, Arbitrum enables scalable and private smart contracts. We use our AnyTrust model. You just need to trust one of the managers of the contract, and then everything will be correct. So it's a pretty reasonable amount of trust. And we have our custom architecture optimized for these small, constant, one-step proofs. So yeah, I appreciate you guys listening to me talk.
Awesome, that is fantastic. I have one question myself.
Yeah.
So from my understanding, the VM is sort of like an off-chain state channel in a sense. So
Yeah.
the managers are players, they all play it.
Yeah.
Okay.
Yeah, I mean, one way to think about the VM is that the VM itself is a state machine. And so we're rather than having your application be a state machine, the state machine logic is pushed into the very lowest level of the infrastructure so that you don't need to think about it anymore. And we can guarantee the size of any state transition will be small.
Cool. And then the managers are sort of like the players as well? Or is there managers and there's users?
So the managers, I mean, this all depends on application, and we're just starting to think about what really makes sense. I think in an example of gaming, then your managers are your players for your game. In the example of you can use this for payment channels, certainly, and there your managers are just the two ends of the channel. I think there's also an interesting use case if you want to have a number of companies maybe that all agree to be managers and kind of the public's willing to trust one of them will be honest. So it depends.
Okay. Awesome, thank you. So, and okay, there you go, Edu. Jump right in.
Yes, about the bisection. So
Yeah.
the messages that you send there, they need to go on-chain.
Yeah, in the worst case, they need to go on-chain. You can also push that off-chain, but at this point, kind of we're in the very worst possible case, so you probably would need to.
Yeah, so if somebody is malicious, probably he will try to get everything to be done on-chain, and the question is who is paying. So let's say you challenge somebody, but he's actually honest, so you start to get him to send all of this list of these N instructions, and who is paying for all of that?
Yeah, sorry, I didn't cover that detail. So when you do a disputable assertion, the asserter makes a deposit. If somebody wants to challenge them, the challenger also makes a deposit. Each step in the bisection protocol, each side needs to make a small additional deposit. And then at the very end, whoever wins keeps all of their funds, and whoever loses, 50% of their funds go to the winner and 50% go to the miners.
I see. And in this list, like it needs if there are n steps, like each step needs the entire state, right? All the registers and the instruction, like you showed, right? It's a long data that you need to put on chain.
It's a very, very small amount of data. So I mean, in each point, you're just putting in a hash of the state.
How come?
So because essentially, like the Merkle tree design that I showed before, the entire each manager in the VM has their own view of what the proper Merkle root is at every step. And so all you need to do is post your Merkle root at step 500, and I either say, well, I have the same root there, or I don't. And if I don't, then the problem must have occurred earlier.
Okay, so, but if it's just a hash of the state, how does the honest party knows? I guess it's what you said right now. Like, how can the honest party?
If the honest party sees a state that does not exactly match what they know is the correct state, then they assume you're wrong. Okay. They don't need to know any more than the hash of the state.
Okay, so if I understand correctly, this transition is done using like explicit inputs of the parties. There are no like hidden inputs or.
Yeah, it's all public. Yeah.
So everybody can compute the transition.
Yeah, it's all public, but you have if you can add hidden inputs through unanimous assertions. If you want to add inputs without unanimous assertions, then you need to put them on chain. So you can use a state channel in order to put input in, if you want to do it at scale.
Awesome. Any other questions? Yep, over here for Jeff.
So obviously one of the big differences between something like state channels or plasma and this construction is that state channels and plasma assume a completely adversarial environment, and you need at least one honest party. Yeah. This does collapse a little bit when like one of the parties in Arbitrum is also one of the parties who is for some reason incentivized to get the correct outcome. So then they can kind of like be their own honest party, be their own one of the group, right? Have you tried to do any work about like identifying the boundaries on these use cases, or like finding like what actually, where this actually will apply in a more adversarial and where it's just a purely, we need to find some trusted person?
It's a great question. So in kind of most of the simplest cases that we've thought about, all the players are happy to just be managers. And so they can just trust themselves, and they might need to also outsource to kind of a server with higher. So the honest available assumption, there is some weakness there. No sort of kind of watchtower construction where your person you're hiring requires only a small amount of state would work for this. Because the managers need to be able to participate in the bisection protocol, which requires the full state of the VM. So I think the easiest applications are things where kind of it's fairly short-lived, or where there's not any risk on the line, kind of in when you're not actively playing. We're still definitely figuring out applications. I think for kind of things that need to run longer. We're definitely still figuring out applications and infrastructure and how this would come in handy at kind of the most,
Awesome.
Be happy to talk more offline.
Yeah, so we'll leave it there, I guess, and you guys can chase Harry afterwards about this. Oh, that's Jason. Did you have a question, Jason?
Yeah, What happens if there's a disagreement on the first step of the computation? Can you still preserve the privacy, or you have to then reveal that step, right?
Well, I mean, you're only at any point you're only going to ever reveal one step. So when the VM is first created, in order to create a VM, it's just initialized with some state, and that any one person can create a VM, and they say the set of managers. And then after that, you can do assertions. You move from it, and any one time when you're doing the bisection protocol, you end up at just a single operation, a single state transition that requires a very small amount of data to be revealed. So yeah, there's never any.
You don't load the input on in the beginning of the computation. In other words, you're. It has to get into the memory somehow. Right?
Yeah. Oh, yeah. So this is another for input. So our assertions are just execution. Actually, providing input is kind of unanimous assertions can trivially just also include input. For disputable assertions, they can't include input yourself. So we have a separate message transaction that provides the input that has to be on chain, that doesn't propose anything for execution, doesn't do anything. It just adds a message to the inbox of a VM. And then the execution actually does the work and takes external actions. So the messages, when you don't have unanimity, the messages do have to be public.
Okay.
But essentially, there's no cost to posting them on chain. You do lose the message privacy there, but you're not paying. You don't need to store them on chain. All you need to store is a single hash. So that transaction would be very cheap.
Okay. Thanks.
Yeah, so you guys can continue that off chain. That's really cool. Thank you very much, Harry, for that. Can we have another round of applause?